Hello, this is the third episode of the series Stochastic Calculus for Absolute Beginners. In this series, we cover fundamentals of stochastic calculus with minimal prerequisites, just basic calculus and probability. Today we will cover the celebrated Ito's lemma, also known as Ito-Döblin formula. This is a stochastic version of the chain rule and the fundamental theorem of calculus in ordinary calculus, so it's very powerful. Before we begin, I would like to know if you're new to the series. If yes, then welcome, and let me know in the comment why you're interested in stochastic calculus. If you have watched any of the previous episodes, I would like to know your thoughts on the level of exposition we've been doing so far. With that out of the way, let's get into the main topic. Let's first recall the fundamental theorem of calculus, aka the Newton-Leibniz formula in ordinary calculus. Consider a function f on the interval 0 to t with continuous derivative f prime. The fundamental theorem of calculus, FTC, states that differentiation and integration are inverse operations. F of t minus f of 0 equals the integral from 0 to t f prime of s ds. In differential form, this reads df of t equals f prime of t dt. And here's a heuristic justification. We first do a Taylor expansion of f and then ignore higher order terms of dt. We write df equals f of t plus dt minus f of t, and the Taylor expansion reads f of t plus dt equals f of t plus f prime of t dt plus f double prime of t over 2 factorial times dt squared plus and so on. The expansion is not rigorous because we're not even assuming the existence of f double prime. But the point is, whatever that follows the linear term f prime of t dt is a higher order term of dt and can be ignored. Rearranging, we obtain the differential form. The differential form of FTC is the origin of the notation df over dt for derivatives. Let's recall why we can ignore terms such as dx squared in ordinary calculus. Here's a simple example, the integral of x over 0 to 1. For each partition, the error in the approximation by Riemann sum is the total area of all the little triangles. The area of each triangle is of order delta x squared. And by summing them up, we see that the total error is of the order delta x. And as delta x tends to 0, the total error shrinks to 0. And therefore, in applied sciences and engineering, when we see a higher order differential of dx, we can ignore it, because their contributions to the integral vanishes in the limit. Just need to keep everything that is linear in dx. And here's the main result of this video. Ito's lemma, it has many versions suitable for different setting. Today we're just going to look at the most basic version. Suppose we have a function f over the interval 0 to t with continuous first and second order derivatives. Let wt be the standard Brownian motion, then f of wt minus f of w0 equals the Ito integral over 0 to t of f prime of ws dws plus half of the Riemann integral over 0 to t f double prime ws ds. The definition of standard Brownian motion and the definition of Ito integrals are given in the first episode. The key feature in Ito's lemma is that we have two integrals, one with respect to the increment of Brownian motion dws, and one with respect to ds in ordinary calculus. And here's a recap on the definition of the Brownian motion. It starts from 0. The path is almost surely continuous. The increment over each interval follows a normal distribution with 0 mean, and the variance is equal to the length of the time interval. And also we have the independent increment property. We recall the definition of Ito integrals. The key is that the sample point for the function x is always the left endpoint of the time subinterval. And the function x must satisfy the so-called non-anticipation property. At any time instance, the value of the function x is independent of the future values of w. We may also write the Ito's lemma in differential form. And this is actually our first stochastic differential equation, or SDE, of this series. It reads df of wt equals f prime of wt dwt plus 1/2 f double prime of wt dt. Note that the ordinary chain rule fails. df of wt does not equal f prime of wt dwt. So why is there an extra term? In short, it's because the paths of Brownian motions are infinitely jagged. They are nowhere differentiable. The derivative blows up at each point. The second order contributions are linear in dt, which is a core lesson of episode 2. So that's the Ito's lemma. We will give a heuristic derivation, followed by examples, and finally a more careful justification, but still not fully rigorous. The aim of the series is to obtain a working knowledge of stochastic calculus, not to track down every epsilon and delta. Let's first start with the Taylor expansion in F, this time with the second order term dx squared. We then substitute x equals wt and dx equals dwt. And then we substitute the key relation in episode 2, dwt squared equals dt. So now on the right hand side we have a dwt, a dt, and higher order terms in dt. In episode 2, we stressed that this formal relation is always understood in the integral sense. That is the integral of gs dws squared, which is defined as the mean square limit of the sum gi minus 1 delta wi squared. And it can be shown that this mean square limit equals the integral of gs ds. And this is what we mean by dwt squared equals dt. Rearranging, we write f of wt plus dwt minus f of wt as df of wt. And then we drop the higher order term in dt, and we get the differential form of the Ito's lemma. And the integral version then follows. Let's look at our first example of the Ito's lemma. In episode 2, we obtained this formula using definitions only. That's the integral from 0 to t ws ds equals half wt squared minus half t. We now show that this agrees with the Ito's lemma. Let's denote f of x equals half of x squared. Then f prime of x is x, and f double prime of x is 1. Substituting f prime, and f double prime into the Ito's lemma, we get half wt squared minus half w0 squared equals the integral ws ds plus half the integral from 0 to t 1 ds. The second term on the left hand side cancels, since w0 is 0, and the integral of 1 is just t. Rearranging, we indeed recover our result in episode 2, which is pretty nice. In our second example, we will integrate an exponential function of the Brownian motion, e to the sigma ws, where sigma is a constant. In the Ito's lemma, let's pick f of x equals e to the sigma x. So f prime of x is sigma e to the sigma x, and f double prime of x is sigma squared e to the sigma x. Applying the Ito's lemma is straightforward, and we have e to the sigma wt minus e to the sigma w0 equals the integral from 0 to t sigma e to the ws dws plus half of the integral from 0 to t sigma squared e to the ws ds. Use w0 equals 0 and rearrange. We have the integral from 0 to t e to the sigma ws dws equals e to the sigma wt minus 1 quantity over sigma minus half the integral from 0 to t sigma e to the ws ds. And the last integral cannot be simplified further. Now that our calculation is done, let's rewrite the result in a different notation. We write xt equals e to the sigma wt. So the result after applying the Ito's lemma now reads xt minus 1 equals the integral from 0 to t sigma xs dws plus 1 half the integral from 0 to t sigma squared xs ds. In differential form, it becomes an Ito SDE. dxt equals sigma xt dwt plus 1 half sigma squared xt dt. And this SDE is an example of the geometric Brownian motion, widely used in financial modeling. We will cover the geometric Brownian motion and some of its applications in finance in future episodes. As mentioned, our final goal of this video is give a more careful justification of the Ito's lemma. But before doing so, let's first recall the proof of the ordinary fundamental theorem of calculus. Partition the interval 0 to t. So we have the endpoints ti equals to I delta t, where delta t is t over n, and I ranges from 0, 1 all the way to n. We then apply the first order Taylor theorem with remainder. F of x equals f of x naught, plus f prime of x naught times x minus x naught plus higher order terms of x minus x naught. Then write f of t as a telescoping sum. F of t equals to f of 0 plus the sum of f of ti minus f of ti minus 1, where I ranges from 1 to n. F of ti minus f of ti minus 1 equals f prime of ti minus 1 delta t plus higher order terms of delta t. Sum over I and get f of t equals f of 0 plus the sum over I of f prime ti minus 1 delta t plus the sum of little o delta t. Pass to the limit. The first sum converges to the integral of f prime of s ds. In the second sum, notice that delta t is of order 1 over n. So summing them up is not enough to offset the n on the denominator completely. So the second term tends to 0, and that finished the proof of the fundamental theorem of calculus. Now let's use the same approach to derive the Ito's lemma. We partition the interval 0 to t the same way, and then we introduce two notations for w the same way we did in the first two episodes. We write wti as wi and delta wi as wi minus 1. It's just for simplicity. Next, we apply the Taylor theorem with a second order term. Substitute x equals wi, x naught equals wi minus 1, and x minus x naught equals delta wi. So we get f of wi equals f of wi minus 1 plus f prime of wi minus 1 delta wi plus half f double prime of wi minus 1 delta wi squared plus higher order terms in delta wi squared. And just like in the proof for FTC, let's write f of wt as a telescoping sum. And the sum now breaks into three parts. Passing to the limit in the mean square sense, the first term tends to the integral of f prime ws dws. That's just the definition of Ito integrals. The second sum, the quadratic terms, tends to the Riemann integral of f double prime of ws ds. That's the main result of episode 2. As for the final sum, it is intuitive to think of little o of wi squared as little o of delta t. And we claim but don't show that this sum tends to 0 in the L2 sense. If you're interested in the technical details, a reference is given in the description. That's it for today's video. If you enjoyed the content, please consider like and subscribe. Thank you very much for watching, and I'll see you next time. Bye.